Greetings, welcome back to the 3n+1 conjecture. Let's see, how did that go? Take any number, if it's odd, multiply by 3, add 1, divide by 2. If it's even, just divide by 2. Do all numbers go to 1? Well, maybe there's a loop that doesn't involve 1, and we've been looking at circuit loops in particular. Given a circuit loop of length k with x up moves, k minus x down moves, there's only one number m that loops back on itself, and here's the formula for that, m. And we're trying to prove that m is never an integer. So for the circuit with 6 up moves and 4 down moves, we can use this table to compute m. The numerator, 3 to the x minus 2 to the x, is 5 times 7 times 19, and the denominator, 2 to the k minus 3 to the x, is 5 times 59. So we know this m isn't an integer because 59 is a spoiler factor. We can't cross it off. 5 isn't a spoiler factor here because it appears in the numerator. However, 5 is a spoiler here and here and here, etc. And if we look at circuits spoiled by the first 1,000 primes, we can knock out about 83% of the circuits. But some of the circuits on this chart are only spoiled by very large primes, like 65,293. So what we'd like to say is that every circuit has a spoiler factor. And we'd like to say that even without knowing what the spoiler factor is. And there's a lot of proofs that work like that. For example, there's a proof that for any n and 2 times n, there's a prime number in between them. The proof doesn't tell you what the prime is, or how to calculate it, or how many primes there are between n and 2 times n. It just tells you there's at least one prime in there somewhere. And we already did a simple proof like that for this table, where we showed that the first column is co-prime with the numerator 3 to the x minus 2 to the x. So every factor in the first column is a spoiler factor. And we can say that without knowing if the spoiler factor in a particular case is 5 or 7 or 47 or what. So let's see if we can grab more of this table of circuits. So whenever x is prime, we notice that every factor of the numerator 3 to the x minus 2 to the x is always some multiple of x plus 1. For example, if x is 7, the factors are 29 and 71. That's 28 plus 1 and 70 plus 1. So all the factors are congruent to 1 mod 7. Now suppose some 2 to the k minus 3 to the x, where x is 7, has no spoilers. Then its factors would be a subset of the numerator's factors, in this case 29 and 71. And since every factor is 1 mod 7, then multiplying them together means the whole 2 to the k minus 3 to the x would also be 1 mod 7. But in most cases, we can show that 2 to the k minus 3 to the x isn't 1 mod 7. For example, not here, not here, not here. I don't show the details, but these are not 1 mod 7. So we can cross off 2/3 of the cells on this row. We know that every one has a spoiler somewhere, even though we don't know what the specific spoiler is. Or take a circuit with 23 up moves and 14 down moves. Since 23 is prime, we know all of its factors are 1 mod 23. But 2 to the k minus 3 to the x isn't 1 mod 7. So we've got a spoiler. And if we check it, we'll find out it actually has 3 spoilers. 5, 21727, and 272927. Now, this method doesn't work when k minus x equals 12 instead of 14 because it's got a spoiler, but 2 to the k minus 3 dx is 1 mod 23. But the method does work for the vast majority of circuits with x equals 23. Okay, so this doesn't take care of all the white cells on this chart yet, but it gives us another approach to work with. Okay, so see you next time.